Well, looks like we can start. Welcome back, everyone, and welcome to week six. 6 of 16. We're getting through the weeks, just 10 more after this one. Biggest announcement so far is our first exam we just got completed. The average grade on this exam was a high 85.2%. The maximum grade obtained was 100%. And it was a pretty short exam. I think for everyone who took it in the classroom, everyone was done before the 30-minute mark. Part of the reason for that is chapter 2 was almost entirely conceptual. We did a little bit of computation, but we were really just seeking to define limits through those technical definitions and seeing how they played out in graphs. So the exam was pretty short because there was a lot of graph problems. The next exams are going to be about the same length, except going through these problems here, we're going from conceptual questions in chapter 3 to, let me try again. We're going from the conceptual questions in chapter 2 about limits to now more computational sort of questions about actually taking more and more derivatives in chapter 3. So the exam is going to be the same amount of problems as the rest of the prior exam, but it might take a little bit of time to compute some of those things. So not every exam is necessarily going to be as short, but my overall goal for every exam written is to try to go for about 50 minutes for the well-prepared student, with another 25 minutes to just check your work, that kind of thing. Aside from the exam, if you took it at the ISU Testing Center, that's this comment here, I emailed it directly to your ISU email address. If that's not an address you check very often, don't hesitate to just send me an email, ask for your exam. I'll be happy to send it over to you. And while we're talking about the exams, we'll always be posting the solutions here, but if you have any questions or comments, I'll be happy to address them. Any questions at all, folks, about the exam or otherwise? Okay, well, for the next part of the announcements, we have our third quiz. This one's an easy one to miss because we fell off the quiz pattern due to the exam week coming out. But we'll be doing the normal weekly quizzes until we get into the next upcoming second exam. And as far as that goes, we're on this week here, week 6. We'll have a midterm week, but nothing crazy is going to be due. There's no midterm exam or midterm quiz. At the end of that week, I'm just going to report your midterm grade, your current standing in the course. Our second exam is going to be right before spring break. And so we're going to get into the entire pattern that we saw before. Right at the end of this weekend here, I'll put out the deferent coverage, the exam review problems, and we'll get through it just like we did before on the last exam. But that's where we're at. That's where we're going. Let me bring that back. Any questions whatsoever, folks, before we get started? Okay, well, we're working through our big chapter on looking into the derivative. We defined the derivative formally in section 3.1, and we looked at how to compute some derivatives in section 3.2 and 3.1. But now we're going to look into finding derivatives in a more fast, reasonable way where we don't always go into the definition of the derivative through the limit of the difference quotient. So all that kind of work begins finally, section 3.3. When you look through these notes, there's a lot of white space here because we're going to just fill out some simple examples as we go. And it feels like it's one big long march of differentiation formula after differentiation formula. But once we get used to seeing what these look like as simple examples, we'll apply them to the larger examples down below here, examples 1, 2, and this one, just more and more derivatives. And these kind of rules really come together very fast. So section 3.3 is not really the reason calculus is difficult. It's more, once you get into section 3.4, section 3.5, we get to more and more differentiation formulas, we start to see that every single formula can be used all together at once in a certain problem or certain kinds of problems. So the difficulty from section 3.3 on is you need to know these kinds of formulas down pat, even though they'll be supplied on the last page of an exam, just so that for extra safety, you could say, not knowing these really, really well can make all of the work in chapter 3 pretty difficult. But let's get started with the derivative of a constant. We looked at this one just by graphing a constant function. We observed that it's always flat. And so the tangent line has to always have slope 0. But the derivative is giving us the value of the tangent line. And so we expect that the derivative of constant should just be 0. For some really random examples, not random, but quick examples, we might have a function that goes y equals, how about 17? So if that's our function, I'll calculate the derivative in blue. We can either call it dy dx or just a y prime. By this formula here, which is stated in Leibniz notation, we would just get a value of 0 altogether. So whenever a constant comes up, that's kind of a nice differentiation formula, automatically 0. There's lots of ways to kind of put some variation on this example. Instead of saying y equals, we could say f of x equals. Instead of something that looks exactly like a constant, like 17, you could put in something more random, like we explored last class, say square root 5. This is confusing because we're going to see how to differentiate a square root function. But because of the lack of x on the right-hand side, that makes this a constant function. And so when we go to differentiate, call it f prime of x or df dx. This one will also be 0 as well. So the trap with a formula here, derivative of a constant function, is we have to be really fluent in identifying constants. Sometimes they're kind of tricky. But if you can just put this in a calculator and get a number out, it's a constant. You can't put that in your calculator if there was an x inside there. You have to plot that. It depends on x. That's what makes it a tougher derivative. But without the x, just an automatic 0. Well, any questions, folks, with that first differentiation formula? Okay, then after that one is the good old power rule. This is called the power rule because we're trying to handle a function that looks like this. Y equals x power n. We refer to this as a power function. But maybe a really quick comment about the power rule. This one is going to be probably the most used differentiation formula in the entire course. We'll see how to do it in the forward direction when we're differentiating, but we have to also reverse it. When we're in the next chapter, chapter 5 on integration, we have to reverse the power rule as well. So many of these formulas that we're going to see here go forwards and backwards, and this is the one we use a lot in reverse. So we use this a lot in chapter 5. We use it in reverse. So we'll come back to exactly what we mean by that when we're way out in chapter 5. But for the moment, here's how to handle the good power rule. So we want a function that looks like this, something to a power. It could be, say, forgot to write examples. This could be simply y equals about x cubed, just an ordinary function. Now, differentiating this using the definition of the derivative, it really is a slog. It takes a lot of algebra to get there. But what the power rule is just saying is, whatever your exponent happens to be, go to the derivative, that's indicated by d dx, or in Leibniz notation by the prime. What happens is the power n turns into a coefficient. So power 3 just comes down in this way. The new power on the variable x is always 1 less. So if we start off on power 3, it drops down to power 2. So that's our power rule right here. Any questions or comments, folks, on using that rule? Okay, so far so good. These are not too crazy as far as differentiation formulas go, but we have to be a little bit careful with this one. This is one that's been highlighted in yellow because of its trickiness. And here's one way the power rule can be just more tricky than expected. Your function could be y equals, maybe it's 1 over, how about the square root of, let's make it a 5th root, why not? X power, How about, let's go with the power 4 on that. So this function right here looks like it does not even fit the requirement of being a power function so that we can differentiate. But really what's happening here is when you see these in practice, in homework problems, for example, we just have to do some exponent work on it really. First thing we can do is say this. If you have a fifth root in your problem, really that's just going to be a denominator going under the power 4 right here. So this is altogether 1 over x to the power 4 fifths. So very first thing you want to do if you have a radical function expression like this, put it back into exponential form. Notice our derivative is written out in exponential form. But second problem here is when this rule is being expressed, the base x is up in the numerator position, not in the denominator's position, and that actually makes a huge world of difference. We need to bring that up to the numerator. So this will turn into x to the power of -4 fifths. So a lot of work, and we haven't even done the derivative on this thing yet, but the exponent surgery finally reveals this right here is the n that's going to be used in the power rule. Any questions at all, folks, getting through the exponent work on this? Okay, well, now that we're here, we're ready for a derivative. Let's call it dy dx this time, just for some variation. And what this is expressing is whatever your exponent is, could be positive, negative, it could be a non-fraction, maybe pi even. Whatever it happens to be, it's now a coefficient. So -4 fifths would go here. The new power on this is 1 less. Well, that just means we're taking -4 fifths. That was the old exponent. The -1 we see here in the formula can be expressed as -5 over 5 for compatible denominators. So we get -9 fifths altogether. And that's the action of taking -4 fifths, subtract 1. And we're now at -9 fifths. So it's a bit messy, but in practice, we didn't do anything different than what we did over here. This just started in a nice place, giving us everything we want. Base x in the numerator, positive coefficient to make it less confusing. But even if it looks wacky like this, with some exponent surgery, you're doing the same exact thing. It's just a little bit nastier because of the fractions as well. I feel like that one right there by the red dot is a pretty tricky one. There's plenty of problems in the homework that go about like this. Any questions at all, folks, on getting through that one? Okay, well, we're getting through some of our main rules so far. The constant rule we use repeatedly. Power rule gets used all the time. And next is the constant multiple rule. The idea with the constant multiple rule is you may have noticed that the derivatives we're taking above have been kind of simplistic. It's been just one term, coefficient of 1 every single time. So now we need to know what do we do with our derivatives if there's a coefficient other than 1, like that c value that's being posted here. But the idea with the constant multiple rule is, let's maybe pause for a moment, go back to the Moodle website, and go back to section 2.4. We're not going to do this often, but I think it's sometimes kind of helpful to express why did we look into all this stuff about limits? How does it even connect with derivatives? The short answer is, well, you use limits to define the derivative. But the more honest answer is, once you're really working with derivatives, you need formulas. And every single formula that's discovered here came from the limit laws. And that's just because, well, again, the derivative of a function is defined in terms of a limit, like we saw in sections 3.1 and 3.2. And take a look at limit law number 3. It says the limit of a constant times a function is a constant times the limit of a function. Well, the derivative is defined in terms of a limit, so it's the same property. This is a limit here with a constant multiplying it. So now the constant goes out in front. Here it is out in front. And that's just a different limit right there. So all of these rules that we're taking a look at, they're really just found by going through these limit laws, write down the definition of the derivative, from section 3.1 or section 3.2 and make that happen by just implying limit law number 3. We won't do the full derivation, but this is just a connection. A lot of the limit laws you see here, for example, limit law 1, limit law 2, are actual properties, sum real, difference rule. There is stuff missing though. The big surprise is there is no limit law 4 that corresponds directly to derivatives. We're going to call that a whole new section, section 3.4, the product rule. We need a whole new section for this one in the quotient rule, because this is not the right formula for derivatives. It gets a little bit more complicated, but at least these were kept here and this as well. So the use of the constant multiple rule for some quick examples could be something along these lines. Let's write out a new function, g of x. G, just because it doesn't always have to be f of x, so slightly different notation. And we could be looking into maybe 16 times x power 1/2. And that would be an ordinary looking derivative. X power 1/2 is just the square root of x, but it was put in a nice way so we can use the power rule directly. We can say next that the derivative of g with respect to x is, well, what is this saying? It's saying that if you differentiate a constant multiplying the function, nothing happens to the constant, it just gets written down. Here it is, written down in this position. Constant stays exactly where it is. Then we multiply by the derivative of the function. So we go times this derivative here, as I get my color going. But when we go to differentiate the function, we're differentiating that part, x power 1/2. So now we're just using the power rule. 1/2 comes down as a coefficient. New power on x is 1 less. So visualize 1/2 minus 1, which means you're really visualizing 1/2 minus 2/2, giving us a -3/2 for the new exponent. So whatever the denominator is, subtract denominator over denominator, and that's a great way to visualize it. New power is -3/2. And all this implies is, well, we're done. We just need to do one quick division. G prime of x is just 8. X power -3/2. And that would be a totally fine answer. Some people might drop x to the denominator to force a positive exponent. But either way you look at it, this would be a correct, acceptable answer. Yes, go ahead. It would be. Where did I get the -3/2 on that? I'm subtracting 2/2 from 1/2. Good eye on that. I think my arithmetic abilities just evaporate over the weekend or something like that. That turns into a -1/2 altogether. So I should have had a -1/2 right here. Good eye on that. It's kind of always embarrassing to get the calculus right, except for messing up the fraction arithmetic. Other questions so far? Okay, so that's the constant multiple rule. It's confusing in a certain sense because when you go to use this rule, the constant has to absolutely be multiplying. If it's not, then this rule takes over and the derivative of that constant goes to 0. So it's as if the only thing that saves your constant is you're multiplying by some valid function of x. So just for another quick look at this, here's another fast example. If we had y equals 52x, then the constant rule does apply to this as well. The derivative of this one, y prime, would just be 52 altogether and nothing else. There's a couple ways to explain this one. 52x is just a linear function. It's a line with a very steep slope, almost looks vertical, but not quite. But this is describing the slope at every single point of the line. That means the tangent line equation has the same exact slope. And so down here, that's the derivative, just 52. But really, there's more things going on here. There's the constant multiple rule. There's a power rule, and that x is really x power 1. When 1 came down and multiplied 52, it's just 52 times 1. The new power of x becomes x power 0, really. But x to the power of 0 is just a 1. So no matter how you look at this, If it's a linear function, you're just getting whatever the slope is, 52 itself. Only works if the original problem was x to the power of 1. If it's something else, then anything else can happen depending on the exponent. So this is a pretty confusing rule because of this part right here. Really has to be multiplying, and if it is, then you just copy in the constant. Any questions at all, folks, taking a look at that one? Okay, so far we've got derivative of a constant is 0. The power rule, this is one we come back to essentially all the time, will be the most learned rule probably in this section. Constant multiple rule is whenever we have something that goes like this. But so far, we don't have anything to help us handle this kind of derivative. Say you want to differentiate that function, f of x equals x cubed minus 5x plus 6. Reason we don't have any rule just yet is because there's really three functions here being all added together. There's a cubic power function, there's a linear function negative 5x, and a constant function being added. We don't have yet any rules to handle that until we scroll just a little bit further. Suddenly we do. The sum rule and the difference rule. Again, these are just side effects of properties of limits, section 2.4. It tells us if you're adding functions, then the derivative of a sum of functions is the sum of the derivative of the functions. And likewise for the differences. But whenever you write down these kinds of rules, you should also come up with a big warning. This does not work. For f of x times g of x, nor f of x divided by g of x. We need section 3.4 to tell us what is the product rule to handle that derivative, what is the quotient rule to handle that derivative down there. We can't just differentiate f, differentiate g, and put them together, in other words. Sadly, it doesn't work out, and it's even worse for division. But pluses and minuses, this is a rare case where it just works out just fine. You can essentially just visualize as this distributes over, and you differentiate term by term, is what it's essentially trying to say. Another thing that's kind of interesting in anything mathematical, when you're defining a formula, think when you define a distributive law, A times B plus C. It's typically just written with two terms, but there's an implication that goes unsaid. Once you define this rule for two terms, it works for any number of terms. Same down here. If you put f of x plus g of x plus h of x, you just differentiate all three functions at once. As long as it's a finite sum, it's going to distribute across, much like this quick visualization here of the distributive law. So for a really fast example, if we take f of x equals, let's take something like that up there, x cubed minus 5x plus 6. Then we can differentiate this pretty rapidly. Well, let's take our time with it. There's lots of rules being used here. When we go down to the derivative, f prime of x, first we differentiate this function right here. We're using the difference rule that says we can split up the derivative across the first two, and then the sum rule to say we can split up across the last one. So we'll just differentiate right here, and that's the ordinary power rule. 3 would come down. New power on x is 1 less, so power 2. And now we just move over to this term. This is still the power rule, but there's more going on. It's a constant multiplying a function, so we're using the constant multiple rule as well. That rule says the constant here is going to survive differentiation because it's multiplying. Because x is to power 1, no x's occur right here. It's just going to cancel off, like in this problem we're visualizing, where it was x power 1, but the derivative is going to be a constant. Then when we go to the plus 6, we have to differentiate that as well. But that's a constant. It will go to 0 in the derivative, so you could put plus 0. But really, when you do a lot of these derivatives, you don't have to say anything. We're just emphasizing it in the notes. The full-on derivative, f prime of x, is 3x squared minus 5. And then we're done. We've got the derivative really, really short order, whereas over here, we were computing a derivative, evaluated it at 1, and that was a big slog. We have to expand things out in a crazy way. And then finally, we got -2. Check out our derivative. If you plug 1 inside here, it's 3 minus 5, you get a -2. Essentially, we did the same exact work of obtaining that -2 by this complicated way by just using the differentiation formulas. If we plugged 1 inside the limit, slope is -2. Plug 1 inside the derivative, we get a -2 slope in very, very short order. But any questions, folks, on seeing these rules so far? Okay, and here's another interesting thought. We go from a function to a derivative. That's the first derivative. But this can just keep on going and going. We can go from the first derivative to the second derivative, f double prime of x. That's because if the original function was provided, the derivative is a function in its own right. You could just derive the derived function. We call it the second order derivative. Any volunteers to say what this one should come out as? Good call. The visualization here is 2 comes down, multiplies, so we've got 6. Power is 1 less of just x. And because that's constant, it's just gone. So that's really all you would have to say, 6x. Does that make sense to everyone so far? Awesome. And just because we can while we're here, let's do it again. I'm running out of colors. I'll go to how about this one. Third order derivative. It gets a little tedious writing out this many primes, so I think we made this comment in last class. You could write the third order derivative this way, or you could just say f parenthesis 3. And actually that parenthesis is really important. Without the parenthesis, you're expressing something different. Function composition, f with itself 3 times. Parenthesis is how we indicate, no, now we need derivative. So third order derivative of f at x, based off this, well, that would just be a 6, right? And it does keep on going forever, but it gets boring beyond this point. We derive one more time, running out of color, so I'll go back to black. It's a lot of primes for a fourth order derivative, so I'll use this notation this time. The fourth order derivative of f at x is just differentiating a constant. So that would go to 0. And then beyond this, we now know that every order derivative is 0 beyond the fourth order, and including the fourth order. So the fifth order derivative is 0, the sixth order derivative is 0, and so on. So polynomials are kind of nice in a way. The derivatives follow a really nice pattern. But the exponential functions that we're going to see next, we have to be pretty careful with. Any questions so far, folks, to this stage? Okay, so here comes the exponential functions. Well, one exponential function, the base e to the x. It turns out that number e, often called Euler's number, is approximately equal to 2.71. We saw it first in the section 2.2 notes, and you probably saw it loads of times elsewhere. That's a really nice base to have for an exponential function. And notice what it's saying on the derivative. This is probably the weirdest derivative ever. It's saying the derivative of an exponential function, that one in particular, is itself. And think about what that's expressing geometrically. It's saying that any point you go on the graph here, plug in the x-coordinate here, and it describes the slope of the tangent line to this graph at that point. You know, I think we need a graph to really say that. Let's say that one more time. I usually try to open this up before class starts, but it's one of those days where I had totally forgotten. So here's y equals e to the x. And now if I go to this point right here, I'm plugging in 0 inside the e to the x function. The output is 1, and it's telling us then that if you do this, imagine that's a perfectly drawn tangent line, slope is exactly 1. And this is not a coincidence. Go to any coordinate here, say this value. It's at 0.5 approximately. The slope is 1.66 approximately. So this is saying, if you plug 0.5 here on the graph to that location, you get e to the power 0.5, e power 0.5. The result is about 1.66. And that would be about, it's hard to get right at that, there we go. That would be the slope of the tangent line at that point. So this function describes the slope of the tangent line to itself at every single point on its graph. That is the only function in existence that does that. Kind of strange in a certain sense. Well, aside from that weird oddity, here's the big danger with this kind of function. We also have the power rule that's working in the background, which says the derivative with respect to x of x to the nth power is n times x power n minus 1. So there's a common mistake when the exponential comes into play. The derivative of the exponential is not x times e to the power of x minus 1. And the reason for that is that only works with power functions. So this formula requires x is the base. Whereas over here, this formula requires x is not the base, it's the exponent. Which makes sense, that's why we called it an exponential function in the first place. It's trying to highlight the role x is playing, it's exponentiating something. So these are suddenly really weird functions. It's also telling us you could differentiate this one as many times as you would like, you're always back to e to the x, whereas the polynomials, if it's of some degree, differentiate enough times, we're back to 0. You know, it's hard to show an example of this one, but let's go for it. Here's one example, y equals e2, let's make it slightly more involved, negative 17 e to the x. If you were to go differentiate this function right here, you would say y prime equals, first is the constant multiple rule. Negative 17 just copies in. Derivative of e to the x is itself. And we're done. Nothing much more to say about that. So really the danger is not the formula itself. The danger with this one is identifying you had an exponential function in the first place versus over here, it was a power function. But let's nonetheless attempt to make one more trickier version of this. If it's f of x equals negative 17 plus e to the x, then in this case, f prime of x would just be e to the x. What makes this example here different than this one was less about that derivative. There's not a whole lot to say or do. Derivative of e to the x is just itself. It's more about, here we use the constant multiple rule. That's why negative 17 survived. Over here, we use the sum rule, and the derivative of constant is 0, and that's why negative 17 is gone. So think of these two examples as one thing that's tricky about the constant rules. It's the multiplication that allowed this to survive, but if you separate with a plus or minus, your constant gets killed off in differentiation. So there's a lot to say about this. Any other questions, folks, about these sets of derivatives? Is always itself, yeah. But now that you mention that, it just depends. We call this one the natural exponential function because it's the only exponential function that has that exact property. The next question is, what if you change from base e to base 2, right? It's still an exponential function. For reasons that we'll get into, our author doesn't derive this derivative just yet. It's because it needs the chain rule to fully explain. But it is an exponential function, goes along with your question. So let's write it in right here. The derivative with respect to x of, let's say, base b to the x. This is the actual big formula that even covers this case right here. We'll see it later on in the notes. This derivative is equal to b to the x, and then there's a little bit more. Multiply it by a constant, the natural logarithm of b, and then you've got the right formula. So if we were to practice with this one, we could say y equals 3 to the power of x. That would then imply the derivative of y prime is, first it's itself, this part, 3 power of x. And then we multiply by natural logarithm of the base. The base is 3, so natural log 3. So that's a derivative we're going to see that does in fact come up really shortly in this chapter. So this is not too big of a preview really. And every time we use this formula right here, really, we're doing the same thing. It's just that e would go inside that spot, and natural logarithm of e is exactly 1. So that makes it the one and only function that simplifies in this way upon differentiation. Every other exponential function has that part that gets tacked on. Other questions so far?
How would you simplify that answer when you just leave it 3x times log or whatever?
Yeah, I'd say that's its most simplified form in that format right there. 3x times natural log 3. Only differences you can really make on this is change where natural log 3 goes. And it's weird where it is, honestly, because we like constants typically to the left. Only reason I wrote it to the right this time is to get around this weird little issue. If you wrote it like this, you have to be just really specific of what is actually the input to the natural log x function. You could do it either with the multiplication or really thinking in function notation, just closing off the input to natural log with an extra parenthesis. Because of that weird side effect, we usually push natural log 3 to the right-hand side, but it's in no way required. Other questions so far? Okay, so this is a good section to come back to, I'd say, because all these differentiation formulas we've seen so far are going to interact with all the new ones in section 3.4, all the new ones in section 3.5, and it can get a bit overwhelming when we have everything on the table. So really, the major goal for section 3.3 is to really learn these rules very well so that when we add a little bit extra, we're not trying to relearn the old rules while at the same time trying to see how the new ones are going. So to that end, we'll do a couple practice problems here, and then we'll see some extra practice down below, where we're just doing derivative after derivative. It's not that exciting, but it's really great practice for what's coming up next in the course. So let's start off with some of these old questions that we've handled before. We've literally done this exact equation. In fact, we just differentiated this function already once today. The reason it's coming back again is because this is an actual common question. But we did it in a really hard way in sections 3.1 and sections 3.2 because we didn't have any of the machinery that we saw up in here in the notes, all those formulas. So we're doing this problem again just as a caution. We do not need the limit formula for a derivative. So the emphasis right here is all about when you see this question come up again and again, it's going to come up a lot in chapter 3. You don't have to do this every single time. You can take advantage of, we now know how to differentiate this function super rapidly. So we're going to skip all of that, which means we're skipping all of that as well, all that work. So here's the step-by-step process for any tangent line equation type problem. Step 1, just calculate the derivative. So if we have a y equals, we could call it a y prime, or we could call it an f prime of x, just depending on the notation you prefer to use. I'll go with f prime of x. Then differentiate it as normally. This will become 3x squared on that term. On this term, we will just get a minus 5. And this term goes to a 0, so we're done with the derivative. Then step 2, we get the slope. We're doing the same kind of steps as we did last time, but we just skipped all the limits. The slope m is going to be equal to f prime at this value right here. Input the x coordinate into the function. F prime at 1 is going to give us 3 times 1 squared minus 5. And so we get a slope of -2 exactly. That means we're essentially done. Step 3 is just the little bit of algebra you would do to finish this all off. The format I usually go to get the actual tangent line itself is y minus y1 equals slope m times x minus x1, or x1, y1, or this coordinate here. So we'll go y minus 2 is the slope, -2, times x minus 1. Now, just about done. We've got y minus 2 is -2x plus 2. So the equation for the tangent line to that curve here at the point 1, 2 is y equals -2x plus 2. And I regret forgetting to highlight these values here. So the role of the derivative in this is that it tells you the slope of the tangent line at any point at whatsoever. So if we want the equation tangent line at 1, 2, we use the derivative by plugging in 1, and now we're totally done with the derivative. The rest of it is just building out that equation. And when we did it in section 3.1, that's exactly what we got. We still got -2, but we were doing it from the very, very first principles. Again, the goal of chapter 2, 3.1 and 3.2 was just to show how the derivative is truly defined. But now that we've done it once, I encourage you, take advantage of the machinery we have in these notes. You don't have to work that hard every single time. I would have to say, for you to do a problem like this, the question would have to say, use the definition of the derivative. I've never asked you to do that specifically on any of those problems, so it looks like it won't even be a common exam question. This one would, doing it in this kind of format. Well, any last questions, folks? Looking at this one a second time.
So for this one, on the left-hand side of the equation, in the second to last one, we have y minus 2. Wouldn't we add that 2 back into the equation to be -2x plus 4?
Oh, geez, yeah, absolutely. That was
Okay,
some really bad math on that.
I was freaking out that I did it wrong. Okay.
Should have noticed it here as well. Thanks for spotting that, Abby. So that should have been plus 4. Let me highlight that mistake right there because that was invisible to me until you pointed it out. And appreciate everyone in the class with those weird little mistakes in person and in Zoom as well. Other questions at the moment? Okay, well, with the correct work right there, we now have the tangent line as fast as possible. Other concepts we want to take a look at are things along these nature. We've done a third order derivative, but this one looks a little bit different on example 2. It's saying calculate f triple prime at -1. Really just an opportunity for us to practice the derivative and doing some evaluations. So let's give this a try next. This is a quartic polynomial, degree 4. And we're calculating the third order derivative, so we should end up at a linear function because this degree goes down once every single time we take a derivative. So to get to f triple prime at -1, it's a journey, but really it's not too bad. You start with the first order derivative, but we want to do that at x. So I would say the trickiness of this problem is you want to leave that off until the very last part. Calculating f prime at 1 is in no way going to get me f triple prime at -1. The reason for that is if I plug -1 inside here, I get a constant. And if I go to the second derivative, it's automatically 0, not the right thing that we're really looking for. So we have to get to that derivative first, but really not too bad. Any volunteers to read out what it should be, just right to left? Exactly. Awesome. So that's the whole process. Power comes down. If there's a coefficient, you multiply it, like the -12. New power is always one less. And that's the pattern for every single one of those derivatives. Next, we'll go to the second order derivative. But any questions at all, folks, on getting that one there? Okay, well, same pattern, just as before. This time 3 multiplies 4, so it's going to be 12x squared. 2 multiplies negative 12, so this is going to be negative 24. Now it's x power 1. And this one is x to the first power. Every time you differentiate that, x just falls off. Or you can think in terms of that's a linear function by the red dot. The derivative of that's just the slope, 36. The derivative of the plus 3 would go to a 0. So that's our entire second order derivative. Then rinse and repeat. Third order derivative next. Notice they get easier as we go. That's kind of nice. The degree's falling down. On this one, we'll get 24x. This is a linear function of slope negative 24. So we would just copy in negative 24. And finally, we're just outputting this all at a negative 1. So let's say here, therefore, by all this work above, the third order derivative evaluated at negative 1 just means the row negative 1 right here. It's 24 by negative 1 minus 24 with value negative 48 altogether. Part of our goal in this chapter, in chapter 3, and more especially in chapter 4, is to say what the role is of the first derivative, the second derivative, and higher order derivatives, what they are saying about the original function f. But for the moment, it's more about practicing just finding them is where we're at so far. Any questions at all, folks, on getting through this one? Okay, we've taken lots of derivatives so far. And the next question is one of those questions where I feel like it's a good one to do even before we do the general practice down below of differentiating function after function. This is a good one because it's kind of trying to say, what is the point to all this? It's an honest application of where derivatives are going to be used. You have an even bigger application in chapter 4. Oftentimes, the best use of the derivative is in some kind of optimization. To find where things are maximized, to find where things are minimized. The derivative is an amazing tool for this. This is more about interpreting what a derivative is once we calculated it. We've done this once, but it was just a graph. So now we're doing it fully analytically with an actual function to model, well, whatever the context is. Let's take a look. It says for the context, biologists have proposed a cubic polynomial to model the length L of Alaskan rockfish at age A. So there's the polynomial. Probably what they did here was they just captured several fish, measured their lengths, approximated their age somehow biologically. Then they would have had lots of points like a scatter plot, and they just fitted a polynomial to that scientific data. So there it is. L is going to be measured in inches. Let's come up with a color for that. A is measured in years. And so when we look at the derivative in this way, dLdA is just saying the derivative of L at time A, but also wants an evaluation when A is equal to 12. So the age of the fish is 12 years old. So think of the derivative as, again, it's a type of speedometer. The speedometer this time is how much the fish is growing, depending on age A. And that's going to absolutely depend on its age itself. So whatever that is has a major influence. First thing we need to do is just compute the derivative. We want units as well. So we're at this part of the process right here. Go where L is. You can either write out L prime if you prefer. I'll go with the Leibniz notation that's already written down, dL dA. I forget I have some color coding going on here. Let me fix that just a little bit. We'll calculate dL. dA, we need to evaluate it when A is 12, but just like on the last problem over here, we wait till we get to that derivative, then we evaluate it. So first, it's all about just evaluating this right here. dA/dL, scientific data is messy. It looks like we have some strange coefficients. Let's grab a calculator as we go. The coefficient 3 is going to multiply that coefficient, so 0.0155 by 3. We have a new coefficient, 0.0465. That was the result of 3 coming down, multiplying, so the new power would be power 2. then it's rinse and repeat once I find the calculator. Over here, power 2 multiplies that coefficient. So we'll write in negative 3.72, negative 0.372, rather, times 2, gives us a negative 0.744. And these get easier as we go. This one's to degree 1, so we just capture the coefficient, plus 3.95. So we're up to this part. Well, that part shaded. We have not yet evaluated it. We'll do that on the very next step. Any questions to this stage so far? Okay, next is the evaluation. So we want to look into the rate of change of the length of this fish with respect to the age of this fish, that specifically, that's the rate of change at any year of this fish. When its A is really close to 0, for example, this is probably a pretty large quantity. It's growing rapidly. When A is getting a little longer, we expect it to get smaller. The fish may not be growing as much, but we want to know exactly what is the rate of growth when A is evaluated to be 12 years. All of this is just a fancy way to say, go up to this derivative, plug in 12 for A. So it's going to be 0.0465 times 12 squared minus 0.744 times 12, then plus 3.95. This is the moment to go back into the calculator. And we've got 0.0465, 12 squared, minus 0.744 by 12, plus 3.95, and altogether, it's a 1.718. Even though this is a little bit weird, I want to put a plus here just to emphasize what we would be writing out when we give the practical interpretation. But one thing I still have neglected to put in is the units for this number, positive 1.78. But it's really not too bad. You go back over here in Leibniz notation, think of it in terms of something per something. The numerator informs us that the units should be inches per, the denominator says years. So Leibniz notation is automatically trying to give us the units. Let's say inches per, I'll just express with a division bar, year. So we just about have it, folks. Finally, this is the hard part of the problem, I'd say, in my opinion. Giving a practical interpretation to what you just calculated is tough. It's easier to come up with a number than to say what it is. But when I said example 3 is a common exam question for exam 2 and the final exam, it's referring to this part right here, giving the interpretation to that number. We have to use the context, which just means we have to mention something about the fact that this is about fish, talking about inches per year. So an interpretation could go about like this. There's multiple ways to say it. I'd probably say it along these lines. Start with the time. It has to be in there somewhere because this value absolutely did depend on time. We could say when the Alaskan rockfish is 12 years old, now what should we say next? Well, this inches per year was just a growth rate. So we can say its rate of growth is this value, 1.718 inches per year. And that pretty much does it. We have the unit of inches and year into the problem. But the thing that's kind of tricky about this is we said its rate of growth. If that was a negative sign, we would have said not its growth rate, but its shrink rate or decay rate, something along those lines. So whatever this sign is informing us if something is speeding up or speeding down along those lines, or growing versus shrinking, that kind of thing. So let's put a really important comment right here. Positive means growth rate. And if it had been a negative, negative means shrink, or any word that just fits the context. I'll go with shrink as opposed to growth. Shrink or compress, anything like that, rate. If we're talking about maybe a rock being thrown up on the planet Mars, positive would just mean it's going up. Negative would just mean it's going down. So the sign of that derivative is always informing you something interesting about the problem. So to get full credit, you have to say something about fish. If you didn't say Alaskan rockfish and you just said fish, good enough for me. The context up here informs what you're talking about. You have to mention the time when it happens. You have to actually say the value of the derivative somewhere. You have to indicate if something is growing or shrinking, going up or going down. And the units would have to be a part of it as well. But if you left those off, it's here as well because of the wording of the problem. So I wouldn't say it's too big of a deal. But think of the things that are highlighted in yellow here. Let's highlight at least that part as required parts for any kind of these interpretations. We'll practice them a lot more because, like we mentioned in section 3.2, these are always pretty tricky. But any questions at all, folks, on this interpretation? Oh, the second derivative would be, let's see, if this is a rate in inches per year, then we would say down below, d2L. So this is how we express the second derivative in Leibniz notation. d A2, so second order derivative, would be expressed this way, or L double prime. It's a little bit trickier in Leibniz notation. 2 here as an exponent means we're taking two derivatives. A here on that variable means with respect to A both times. That's weird because if we have a function with more than one variable, say A, X, and Y, you could be taking a second order derivative with one variable and then again to the other variable, as weird as that is. But on a fundamental level, the first derivative is just a rate of change. The second derivative is a rate of change of the rate of change in units. Inches per year squared. So what this is informing us is how fast this is increasing or decreasing. It's like the acceleration behind its growth rate or its shrink rate. And then this kind of game goes on forever. You can now talk about the third order derivative. It'd be the rate of change of the rate of change of the rate of change. And it's telling you how this is changing here. So it's always kind of a weird game that goes on. But notice how the unit changes as well. The unit is originally inches per year. Each time we do a new derivative, it's a new per year. But then we write it in a more simplified way of just saying inches per year squared, even though that seems kind of weird. That's what the unit becomes. Does that make sense with that question there? Awesome. That's a great question as well, because we have to think about how the second derivative is informing something about the problem, just as the first derivative is. We'll be involving in chapter 4, the original function, the first derivative, and the second derivative can all be used at once in one single problem. Other questions or comments so far? Okay, so it's not a big application, but these kinds of problems are just trying to get us to that point where once we're in chapter 4 doing those applications and we take a derivative, these are the kinds of thoughts we should be thinking. This is the meaning behind each time we do those derivatives. And with what we got left in the notes, really it's just a practice doing some derivatives. So this is the major part of the actual homework assignment in WebAssign, doing lots of these down below. There'll be a problem about like this one as well that's applied, something like this, doing higher order derivatives, and then a lot of this kind of stuff. So this is just our opportunity to practice differentiation. Let's give it a try. First one is just a y equals, so we can go y prime, or let's give it Leibniz a little bit more love. Dy dx is just as valid. The number came on here because now we're using the power rule is exponent 4 multiply 6. So it's a negative 24. New power on x is power 3. Same game over here, we'll get plus 6x on this one. And then suddenly this one's dangerous. Any volunteers to say what the derivative of that should be? Sorry, say again. It wouldn't be negative e to the 4th on this one. This is one of those really nasty ones we have to watch out for. It wouldn't be negative 3 cubed either. This one is, again, one of those problems that are just really strange and tricky in a certain sense. One thing that helps though, if you see something weird like this, think, what would the graph look like? What is the graph of just e power 4, in other words? If it were y equals e power x, we have a graph that goes like this, and the derivative is just e to the x. But if you go e power 4, your graph is really just this. It's just a constant function. That means the derivative of this one is just on automatic 0. You're really just differentiating that function altogether. So it goes plus 0 from this one right here, only because it's a constant. So again, those are really nasty in a certain sense. Lots of stuff look like they're functions that depend on x, but they're really constant. Watch out, for example, things that look like this. Y equals natural log 7, y equals e to the power 4, y equals maybe something like, I think I'm running out of examples, but those would be some common ones to watch out for. Maybe one more. Y equals, maybe it's the 5th root of 7 cubed. The common feature with every one of these functions is x is missing on the right-hand side. It doesn't matter how fancy we make these functions. Every one of them has y prime 0. Oh, let me fix that right there. That means on this one right here, we're pretty much done. It's standard form to simplify the function as we go, so I'd probably take one more line to just say plus 0, didn't change anything at all, and we're down to that line there. Well, we've got it, folks. That's our first derivative on the larger set of practice problems. Next one is not as friendly, but we'll get through it. Any questions at all getting through this one? Okay, the danger on this one right here is, although we can find the derivative of square root of x, the derivative of 4x minus 3, the derivative of x minus 3, finding those derivatives doesn't actually help us at all in this problem. It's kind of weird, because the derivative of a product is not the product of these derivatives. So whenever this happens, this is what the comment up here is about. We just have to do some light algebra to correct these, get them into this kind of format, for example, and then we go term by term differentiation. In the next section, we're going to come up with a product rule that would allow us to differentiate that in that format. But even with the product rule, the strategy of just expand this out is still a great one. We reserve the product rule for functions you can't expand out and put in this format. Think x times e to the x. No help on that one. But if you just fully FOIL all this out, this will be a fun one to differentiate. If you knew the product rule, this is a nasty one to go through if you used it directly. So let's take some time on this and just work it out algebraically. Very first correction, we probably want to re-express that root x and say f of x is x to power 1/2. Next thing we want to do is expand the expressions on the right. So I'm going to FOIL out 4x by x, 4x by negative 3, turn it around and distribute this way, so minus 3x. This way will be plus 9. Now we're looking at x to the 1/2 power, 4x squared, sure, but we're going to distribute 1/2 power inside here. So let's rewrite x squared as power 4/2. The 4/2 gets us back to x squared, but now it has compatible denominators for when we distribute further. Likewise, this is negative 15x, but we can call it negative 15x to power 2/2, same thought, and then plus 9. Still, we're still not done with the algebraic surgery on this function, but this is our big step. Distribute this in. When you multiply here to here, you will get 4x times the powers a half plus of 4/2, so they add together. So 5/2 on this one, minus 15, x to the power 3/2 on that one. And last arrow, this one's just 9 times x power 1/2. Now that we're to this stage, it's like one of these problems once again. We're just going to differentiate term by term. I think the algebra sometimes is interesting because sometimes the calculus is the easy thing. The algebra is the tricky thing, depending on how much practice you've had. Any questions at all, folks, on writing down to this line here? Okay, so the strategy here is expand first. Now, when we go to differentiate this thing, constant multiple rule says this 4 stays right where it is. Power rule says 5/2 will multiply it. The new power is 1 less, so if the denominator is 2, just subtract 2/2 from that, and we get down to 3/2. Notice we have to do a little bit of work here. It simplifies a little bit, but nothing too major. Then rinse and repeat. Next term goes exactly the same as the first term. Constant multiple rule says 15 stays where it is, multiplies the exponent. The power updates, subtract 2/2. New power is 1/2. And then we do it all over again. So copy plus 9. Power 1/2 is going to multiply it. Subtract 2/2 to get a new power. Negative 1/2. And that's the right derivative. All we now need to do is some simple simplifications. We have 2 canceling into 4, leaving 10. X power 3/2. Nothing too major here. I'm just going to multiply through the numerators. So negative 45/2, x power 1/2. Or you could call that square root of x at this point. Really, the formatting here is kind of all up to you. Next thing, plus 9 halves x power negative 1/2. Even this one, if you wanted to, you could drop down to the denominator and call it a square root. But I'm not too worried about how you express your end answers. If you give me something with negative exponents like these, I'm always totally fine with it. And so is WebAssign as well. We're not too picky about that. Well, any questions at all, folks, with part B? Slightly more tricky one. Okay, I just want to make an extra shout out to one particular derivative. The derivative of this function, y equals root x. In our application section, this is actually a derivative that comes up a lot. Part of the reason is square roots are used to help us find distances of things, and that's automatically a great application in calculus, distances being one of them. So getting a good derivative on this one is a good idea. Here's what it looks like from first principles. You'd rewrite the exponent as 1/2 because it was a square root. When we differentiate, 1/2 comes down. The new power is negative 1/2. But then you can start doing some work on this. You can drop the base x into the denominator. And if you wanted to, you could make this a square root again. 1/2 root x. And so what all this implies is we have a pretty cool little formula. Not a formula that you have to memorize or even worry about, but it's something that comes up a lot. So it's a good one to think about. The derivative with respect to x of square root x is 1/2 root x each and every single time you do it. So you can go through the motions here, or that's a handy formula we'll shout out to and use a couple times in the notes. Well, we did it, folks. It looks like we have just a couple more to take a look at before we call it a day. Let's maybe make the next couple our last ones. Any questions at all so far? Okay, some of these problems I put down in the notes just specifically because there's something very similar to this one in WebAssign. We did something similar to this one, and this is one of those tricky problems. We know we need to use this formula. This is the power rule. We've already used it a few dozen times at this point in the class already. And although it applies to here, you would never want to use it directly with your bases in the denominator. So very first step you want to take here is rewrite with base t in the numerator. So we would get y equals 9 times t to the power, now positive 2/2. Once we get down to here, it now fits this directly. Now you could rewrite a power rule for when your base is in the denominator, but I think it's not a great call to have two different rules you have to worry about. If you can just force your exponents in the right position, now it's just one rule. I think it's a lot less memorization and trickiness as well. So if you prefer this strategy, you can say dy dt, or just simply y prime, it's going to be the results of 9 times 2/5 times t. Throw that down to the denominator. The newton power of t is 1 less. So we're subtracting 5/5 to get -3/5 on this one. And that means we're essentially done. This comes out as 18/5 t to the power -3/5. And nothing further to say on that one. Well, any questions, folks, on that derivative there? It's kind of weird how some of them go fast, some of them are a bit of a slog. It's kind of like that in WebAssign as well. The questions are not necessarily ordered from slowest to fastest. It's more of a look before you leap kind of situation. Idea with part B is you always want to expand these out. Part C, force your exponent space to be in the numerator. Part D is just expanding on that. But if you're the kind of person that works ahead a little bit further in WebAssign, watch out for part E as well. On this one, you have to divide all terms by square root of x, simplify. And aside from that, I think we've gotten through the major things that are pretty tricky on the WebAssign problems. It's still a tricky section, so if you want to wait till we finish out all of these notes, totally understandable. But you could get started today and make some pretty good headway at 3.3. Before we call it a day, let's do this last question right here. Something like this, I believe, is also likely to come up in WebAssign, and it's the trickiest one in the whole set. Any volunteers for what that derivative should be? Good call. We're just looking at an overall constant here. If there's no x on the right-hand side, 0 immediately. So watch out for those as well. I think those are the frustrating ones. Well, have a great afternoon, folks. When we come back on Thursday's class, we'll finish off these notes in short order and then look into the product rule, quotient rules.
So I have a question. For the quiz that you want us to do on Thursday,
Yeah.
can we solve it this way with taking the derivative instead of the
Oh,
previous?
yeah, absolutely.
Okay. All right. Thank
It's a
you.
weird quiz, right? Because we're kind of between methods. So sorry, let's try to
Right.
open that quiz and
And if
missing.
that one's that way is a little bit easier.
Yeah, absolutely.
Okay.
So there it is. Finally took me a bit to get there. Yeah, with the wording here, any method that you use that works here is going to be totally fine.
Okay, perfect. I just wanted to double check. Okay. Thank you.
Yep. Have a good one.
You too.